Faraday's ice pail experiment is a simple electrostatics experiment performed in 1843 by British scientist Michael Faraday that demonstrates the effect of electrostatic induction on a conducting container. For a container, Faraday used a metal pail made to hold ice, which gave the experiment its name. The experiment shows that an electric charge enclosed inside a conducting shell induces an equal charge on the shell, and that in an electrically conducting body, the charge resides entirely on the surface. It also demonstrates the principles behind electromagnetic shielding such as employed in the Faraday cage. The ice pail experiment was the first precise quantitative experiment on electrostatic charge. It is still used today in lecture demonstrations and physics laboratory courses to teach the principles of electrostatics. Description of experiment. Below is a detailed modern description of the experimental procedure. The experiment uses a conductive metal container A open at the top, insulated from the ground. Faraday employed a 7-in diameter by 10.5-in tall pewter pail on a wooden stool, but modern demonstrations often use a hollow metal sphere with a hole in the top, or a cylinder of metal screen, mounted on an insulating stand. Its outside surface is connected by a wire to a sensitive electric charge detector. Faraday used a gold leaf electroscope, but modern demonstrations often use an electrometer instrument because it is far more sensitive than an electroscope, can distinguish between positive and negative charge, and gives a quantitative readout. The container is discharged by connecting it briefly to a large conducting object, called a ground. This can be done by touching it with a finger, using the conductive human body as a ground. Any initial charge drains off into the ground. The charge detector reads 0, indicating that the container has no charge. A metal object C is charged with electricity using an electrostatic machine and lowered into the container A without touching it. As it is lowered, the charge detector's reading increases, indicating that the outside of the container is becoming charged. Once the object is well inside the lip of the container, the charge detector levels off and registers a constant charge. Even if the object is lowered further, the charge on the outside of the container is the same polarity as that on the object. If the charge detector is touched to the inside surface of the container, it is found to be charged with opposite polarity. For example, if the object C has a positive charge, the outside of the container A will be found to have a positive charge, while the inside of the container has a negative charge. If the object C is moved about inside the container without touching the walls, the charge detector's reading will not change, indicating that the charge on the outside of the container is not affected by where the charged object is inside the container. If the charged object C is lifted out of the container again, the charge detector will decrease to 0 again. This shows the charges on the container were induced by C, and the container has no net charge. Therefore, the opposite charges induced on the inside and the outside must be equal in size. The charged object C is touched to the inside of the container. The charge detector reading does not change. However, if the object is now withdrawn from the container, the reading stays the same, indicating that the container now has a net charge. If the object is then tested with the charge detector, it is found to be completely uncharged, and the inside of the container is also found to be uncharged. This indicates that all the charge on C has been transferred to the container, and has exactly neutralized the opposite charge on the inside surface of the container, leaving only the charge on the outside. So the charge on the inside of the container was exactly equal to the charge on C. kits are available from educational supply firms containing all the apparatus needed for students to perform the experiment, preventing error due to stray charges, stray static electric charges on the experimenter's body, clothes, or nearby apparatus, as well as AC electric fields from mains-powered equipment, can induce additional charges on parts of the container. A charged object C, giving a false reading. The success of the experiment often requires precautions to eliminate these extraneous charges. Any charges on the container and nearby conductive objects should be removed before the experiment by grounding, touching them briefly to some large conducting object called a ground. Any charge on the object will flow into the ground due to its mutual repulsion. This can be accomplished by touching them with a finger, using the conductive human body as a ground. However, the experimenter's body itself should be grounded frequently by touching a good metal ground such as a metal workbench, or preferably a water pipe at the grounding wire of the building's mains power wiring. Ideally, the experimenter's body should be grounded throughout the experiment. Some demonstration kits include conductive ground sheets which are laid on the workbench under the apparatus, and anti-static wrist straps the experimenter wears during the experiment which are connected to a good ground. The electrometer measures charge with respect to ground, so it requires a connection to ground during use. It has a ground wire, usually colored black, ending in a clip which should be attached to a metal ground during use. The experimenter should avoid excessive movement during the experiment. Walking around or waving his/her arms can cause the buildup of static charges on clothing. The experimenter should hold the handle of the charged object C as far from the object and the container as possible when lowering the object into the container. In professional student laboratory kits, the container A is often in the form of two concentric cylinders of metal screen open at the top. A screen acts the same as a solid metal sheet for electrostatic charge, as long as its holes are small. The inner cylinder is the Faraday pail container itself, separated from the outer cylinder with insulating supports. The outer cylindrical metal screen surrounds the inner and acts as a ground to shield it from stray charges. This design largely eliminates the stray charge problem, as well as allowing the experimenter to see inside the container. The electrometer ground lead is clipped to the outer ground screen, and the experimenter touches this screen while performing any procedure. To ground the inner screen, the experimenter can bridge his finger between the inner and outer screens. When doing this, it is important that he lift his finger first from the inner screen, not the outer, to avoid leaving charge on the inner screen. Charge can leak off the charged object C in the container along handles and supports due to surface layers of dirt and oil from fingerprints. If this is suspected, the equipment should be washed with detergent to remove oils and dried. When measuring the charge on the inside or outside surface of the container, the charge detector should not be touched to the surface near the lip of the container. Extra charge concentrates near the edge of the opening due to the geometry of the metal. Further experiments. Alternate procedure. An alternate way of conducting the experiment. After the charged object C is lowered into the container in procedure 2, the outside surface of the container is momentarily grounded. The charge on the outside of the container all drains off to ground, and the charge detector declines to 0, leaving the charge on the inside of the container equal but opposite to that on C. Then the object C is removed from the container. Since C is no longer present to hold the induced charge on the inside surface of the container, it migrates to the outside of the container, so the charge detector registers an equal but opposite charge from its previous reading. This new charge can be proved to be equal and opposite to the charge on C by touching C to the exterior surface of the container. The two charges exactly electrically neutralize each other, so both the exterior of the container and sea are found to be uncharged. Non-contact charge measurement. Lowering an object into a Faraday container offers a way to measure the charge on it without touching it or disturbing its charge. The charge induced on the outside of the container by charges inside it depends only on the total charge inside. If several charged objects are lowered into the container, the charge on the outside will be equal to the sum. Charge addition. If several conducting charged objects are lowered one after the other into the container and touched to the inside, all the charge on each object will be transferred to the outside of the container, regardless of how much charge is already on the container. This is the only way electrostatic charges on objects can be added together. If two conducting charged objects are simply touched together on their outside surfaces, the charge on both will merely be shared between the two objects. This is how charge is transferred to the top terminal of a Van de Graaff generator. The terminal is a hollow metal shell and functions as a Faraday pail. Charge is transported inside it on a moving belt, then removed from the belt by a wire attached to the inside of the terminal. Since the inside of the terminal is at a constant potential, the charge from the belt flows to the outside surface, adding to the charge there, regardless of how much charge is already on the terminal. Contact electrification produces equal charges. The charge summing property of Faraday's pail can be used to prove the contact electrification. Charging objects by rubbing or touching them together produces equal and opposite charges. A piece of fur and a piece of rubber or plastic are first discharged so they have no charge. Then both are lowered together into the container attached to non-conductive handles. The charge detector registers no charge. Then they are rubbed together inside the container. The rubbing will cause the fur to become positively charged and the rubber to become negatively charged due to the triboelectric effect. However, since this is due to a separation of equal charges, the two charges are equal and opposite, so the sum of the charge on both objects is still zero. This is proven by the charge detector, which continues to read zero after the operation. The charges on the individual objects can be demonstrated by removing one at a time from the container. The charge detector will register opposite charges for each remaining object. Multiple concentric containers. In his original 1844 paper, Faraday also investigated the effect of using several conducting containers one inside the other. He found that the induction effect works through multiple containers the same way it does through one container. He used 4 pails, each supported on a non-conductive pad inside the next. If a charge is lowered into the innermost pail, an exactly equal induced charge will appear on the outside of the outer pail. The charge on the outside of each pail induces an equal charge on the next. If one of the pails is grounded, the charge on all the pails outside it goes to zero.